Welcome to this recorded session on graphs. This is our second session. In our previous session, we talked about the fundamentals of graphs. We defined graphs, and we also talked about some fundamental properties, types, and representation of the graphs. So if you recall, like the fundamental definition included that we notate graph as a collection of vertices. We use capital V to notate set of vertices. We use capital E to notate set of edges. So VE is a collection which represents the graphs. Graphs are composed of vertices and edges. And then we talked about different kinds of graphs. Graphs might be directed ones or undirected graphs. We talked about their representation. We talked uh, about two kinds of representations. One was adjacency matrix and the other one was adjacency list. So in our today's discussion, we'll be getting introduced to some more fundamental concepts about graphs, and we'll be talking about some applications of graphs. So let's start with the first characteristic which can be there inside a graph, which is related to graph connectivity. And within connectivity, we are about to talk about a walk. So a walk in a directed graph is a sequence of vertices, V1, V2 up till some kth vertex. So when we focus on the definition, it's a sequence of vertices. That means that we have a mechanism to go from one vertex to the next vertex. So for example, if you have to go from V1 to V2, then there should be an edge. There should be an edge from V1 to V2. So Vi, Vi plus 1 is an ordered pair. And last time we studied that one ordered pair in a directed graph represents a directed edge. So in this entire sequence, so if you pick any two consecutive vertices in the sequence, that means that there is an edge from the starting vertex to the next vertex. And we just follow the successive edges. So that sequence of edges gives us a walk. In other words, we start from a particular vertex, and by using those edges of adjacent vertices, we can walk inside a graph, or we can access other vertices from one vertex. So if we focus on these 6 vertices, so we are at A, and that's our start point. So from A to D, we use the edge AD, and in our walk, we go from A to D. Then we go to E. We start from D and go to E. Then we go to C. So why we are putting them in a sequence? Because they have edges which are like taking us to the vertices which are on the other side. And then from D to B, we have a walk. So a walk is a sequence of vertices, and the red list of vertices at the end is a sequence, right? So why we are emphasizing over here on sequence? Because if you pick any pair of vertices which are next to each other, so DE must be an edge in the set of edges. So DE is an edge. So that's why we were able to take the walk from D to E. And we can expand the walk. We can add more vertices in the walk. Length of the walk is number of edges which we use in the walk. Path is another characteristic related to connectivity. So path in a directed graph is a sequence of vertices. The restriction on walk is that repetition is not allowed. So that means that we can't go back to the same vertex which we have already visited. That was not the restriction in case of walk. So if you look at the same graph that we used in our previous example of walk, we start from A. So A, D, E, F is a path, and none of those vertices is being repeated in the sequence. Number of edges in the path are also called length of the paths. So the claim or the characteristic or the theorem related to directed graphs is that the shortest walk between U and V is the path. And we can prove this claim using contradiction. We assume that it's not a path, but it's still a shortest walk. So suppose it's not a path. So if it's not a path, some vertex R is repeated. So when vertex R is repeated, that means that this is a walk, but not a path, because repetition is allowed over here. When we get rid of the repetition, uh, we are left with something which is the shortest possible way of moving from U to V, and that gives us the path. So the first ICP will start from 1436 in this recorded session. So you have to submit the ICPs on the same protocol as you did for the previous recorded session. You'll have to solve them on paper, and then we'll be accepting the uploaded solutions correctly numbered against each ICP to LMS. So write down uh, this line of argument in a formal way. Closed walk is a walk that starts and ends at the same vertex. So closed means that we started from a vertex and our target is to go back to the starting vertex. So if we start from A using a sequence of vertices, repetition is allowed because it's a walk, but our target is that we started from A and we are ending at A. A path that does not contain repeated vertices, but a path that starts and ends at the same vertex. In that case, the only exception is that the last vertex is getting repeated, which is fine. So we call that kind of path a cycle, where first and last vertices are same. So we start from A, we go back to A. So with the exemption of A, which is the start and end vertex, the intermediate vertices cannot be repeated because it has to follow the characteristics of path as well. So that's the starting and the last or ending vertex are the exemptions over here. They are exempted from the fundamental definition of no repetition. Okay. The shortest closed walk from U to V is a cycle. So we have to expand the same analogy as we used for the shortest walk from U to V is a path. So when we say closed, that means that we are allowed to go back to the starting vertex. And in this ICP, you are supposed to write the formal lines of argument to prove this claim that the shortest closed walk from U to U, from a vertex to itself, is a cycle. Okay, now we are like trying to focus on connectivity a little more. In an undirected graph, a pair of vertices U and V are connected if there is a path between U and V. What is a path? So we have just studied that path is a sequence of vertices where repetition is not allowed. So path from U to V will be a sequence of vertices where none of the vertices is repeated. So if we have some mechanism of reaching from U to V, then U and V are connected. So a pair of vertices is connected if there is a path between those two vertices. Okay, just for the sake of clarification, we should not be mixing up this thing with adjacent. In our previous session, we talked about adjacent vertices. So adjacent vertices are the vertices which are immediate neighbors, which means that there is a direct edge from vertex U to V. So if two vertices are adjacent, then definitely there's a path from U to V of size 1. So size of the path is 1 because those two vertices are adjacent and only one vertex is required to create that path or to traverse or walk along that path. But the converse is not necessarily true because if U and V are connected, that does not mean that they are always adjacent. They may be adjacent, may not be adjacent. For example, if our first vertex is U and there is some other vertex in between and then we have a vertex V. So there is a path from U to V, but U and V are not directly connected. And the similar analogy can be deduced for undirected graphs. Okay, so now we have like a lot of very simple, very easy, but very important ICPs to clarify the fundamental notion of connectivity. So look at this graph. After each question, try to pause the video and answer these questions as yes or no questions. Are C and D adjacent? So if you look at C and D, they are adjacent because there's a direct edge from C to D. So answer is yes. Are C and D connected? Yes, because if they are adjacent, then they are connected. We are using this fundamental principle which we have just studied over here, that if they are adjacent, then they are connected as well. So the answer is yes. Are A and G adjacent? If you look at A and G, so there's no direct edge between A and G. So they're not adjacent. The answer is no. After each ICP, I would strongly suggest that before jumping to my solutions, try to figure out the answers yourself, and then it will be quite productive and helpful to understand the concept. So you can verify those answers later on because I'm solving some of the ICPs. Or ING connected, so we need to, because they're not adjacent, but there could be a path from A to G, so we just need to figure out a path. So there's a path from A to G. In fact, there are multiple paths from A to G. So this red line is one possible path. Another alternate path could be that from A to D and then we go to G. There could be more paths. So for example, if we start from A, we go to B, go to H, go to F, E, and G. So, and there are, in fact, there are many paths. So A and G are connected. The answer is yes. In an undirected graph, a pair of vertices is connected if there is a path. So are C and D adjacent? So answer is yes. There's a direct edge from C to D. Are they connected? Again, yes, because they're adjacent. Are B and C adjacent? Answer is no, because there is no direct edge between B and C. Are B and C connected? Yes, there's a path from B to C. Are A and E adjacent? So now this is a slightly different kind of example. So if you focus on A, it is here, E is here. So they're not adjacent because there's no direct edge from A to E. Are A and E connected? They are not connected because there is no path which can take us from A to E. And this whole thing is one graph. Are F and G connected? So yes, F and G are connected and they are adjacent as well. Are B and C connected? Yes, because there's a path from B to C. Is every pair in the graph is connected? The answer is no, because we can show presence of a pair which is not connected, which means that if you focus on DF, this is a pair of vertices where there is no path from D to F. So the answer is no in case of is every pair connected. So not every pair is connected. There are multiple pairs which are not connected. And when we say every, that means there are questions about for all. If we show no for one possible pair, so our entire answer is no. Is the graph connected? So now in order to answer this question, focus on the first definition. An undirected graph is connected. An undirected graph is connected if all pairs of distinct vertices are connected. So if there is a path from every vertex to every other vertex, let me say it again. If there's a path from every vertex to every other vertex, that means that the graph or the underlying undirected graph is connected. So in this case, we have just demonstrated presence of a pair where there's no path. So all pairs, so it's not true for all pairs because we were able to demonstrate presence of a pair which falsifies this claim. So the answer is no, the graph is not connected. Look at the next graph. Are A and G connected? If there's a path from A to G, that is connected. That's similar kind of ICP we have solved in our previous slide as well. So the answer is yes. Is every pair connected? Yes, every pair is connected. And is the graph connected? Yes, it is connected because it fulfills the definition of connected graph, which is written on top of the slide. A graph is connected if all pairs of the distinct vertices are connected. So hence the answer is yes, that the second graph is connected. So now what we know is that what is a connected graph? A connected component of a graph, particularly undirected graph, is a connected subgraph which is maximal in size, which means that every possible connected vertex is included. So maximal means maximum possible. A connected component of a graph, of an undirected graph, is a maximal connected subgraph. Let's try to understand this concept using an example. So if you focus on this graph, this is the same graph that we've used for some of the ICPs in our previous slide. So these red dotted lines around two sets of vertices show the connected components. So the left one is connected component number one, the right one is connected component number two. So this graph has two connected components. Each component is a maximal connected subgraph. Let me try to clarify this concept a little more over here. So if you focus on these two vertices, A and C, they are connected. Is it a maximal? This is a connected subgraph, but is it a maximal connected subgraph? This is not maximal because we can bring in more vertices into this and we expand its size to three vertices. So this group of three vertices is a connected subgraph of the original graph, but is it maximal? The answer is no, because we can expand it further and we can add fourth vertex, which is D vertex, and we make it a connected component. We make it a connected component because it's maximal. Why is maximal? Question is that after figuring out these four vertices, A, B, C, and D in this component, can we add more vertices into this such that such that every possible vertex is connected with other vertex over there? The answer is no, because if we try to bring in E in the component, E will not be connected with C or rest of the vertices. Same will apply for F and G. So this left block, which has already been enclosed in these this dotted polygon over here, and the third one is what is we have on the right hand side. Both of them are the connected components, but they are maximal because they are maximal connected subgraphs of the original graph. No further vertex can be included in these components such that the graph or the subgraph remains connected. So if someone asks us that what is number of connected components of this graph, so number of connected components of this graph is 2. So connected components of G and their cardinality is 2. Is this graph connected? The answer is no, because there is no path from C to E or C to G and many more such pairs. Is the subgraph induced by EFG connected? Induced is a term which we studied in our first session of graphs. So by induced subgraph, we mean that the graph which is composed of or constructed over EFG, is this subgraph connected? So yes, the graph which is induced over these three vertices, within that group, those three vertices are mutually connected. So the answer is yes. Is the subgraph induced by EFG a connected component? What is a connected component? So connected component is a subgraph, is a connected subgraph which is maximal. Can we add any further fourth vertex in EFG? The answer is no. So yes, it is a connected component as well. Is the subgraph induced by ABC connected? If you focus on the subgraph induced by A, B, and C, so that is this part of the graph. So sorry for the poor drawing. Let me draw it once more. So these three vertices connected? Yes, because there's a path from any vertex in that group to any other vertex in the same group. So the answer is yes. Is the subgraph, the same subgraph induced over A, B, and C, is it a connected component? So connected component is a connected subgraph which is maximal. So is this component maximal? The answer is no, because we can add a fourth vertex and we can still keep it connected. So the answer to the last ICP on this slide is no. we have talked about that how a pair of vertices is connected. We talked about connected graphs and we talked about connected components. So for directed graphs, a similar kind of analogy will be replicated, but because the direct edges are directed, there are explicit directions on edges. So in a digraph, in a directed graph, U and V, a pair of vertices are strongly connected if there's a path from U to V and there's a path from V to U. Why we are talking about those two explicit paths? Because edges are directed. So if we have two vertices, there is path from one vertex to another one. So let's say first one is U, the other one is V. So if there is a path from U to V, so we can't call that space is strongly connected because there's no path from V to U. So if we have a path from V to U, now both ways connectivity is there, both ways paths are there. And this pair of vertices is a strongly connected pair of vertices. Is there a path from A to E in this ICP? The answer is yes. There's the path through C which takes us to E. Is there a path from E to E, E to A? So if you focus on this part, there's a path from E to A. The answer is yes. So if both ways paths exist, what can we call that pair? And that is the next ICP. Are these two vertices strongly connected? The answer is yes, because they fulfill both of the conditions of the previous two ICPs. Look at the next graph. Is there a path from A to E? Now, some directions have changed over here in this example. So if you focus on A, there is no outgoing edge from A. So there's no way to go out of A. In other words, there's no way from A to E. There's no path from A to E. So the answer is no over here in the first part. Is there a path from E to A? The answer is yes, the same answer as that of 1461. And is this pair strongly connected in the second graph? The answer is no, because it does not fulfill the existence of path in both directions. Okay. Are C and D strongly connected in this graph? Let's first solve the ICP. So if you focus on C, D, so there's a path from C to D. This is one-way path. So in order to check strongly connected pair, we need to figure out the path from D to C as well. So let me change the color. So from D to C, if I go to B, A, and then C, so yes, there's the path that exists from D to C and C to B. So this pair is strongly connected. Answer is yes to this first IC. Are all pairs strongly connected? So we need to look at all pairs, which means that can we go from any vertex to any other vertex? If that's the case, then all pairs are going to be strongly connected, which means that there will be path from every vertex to every other vertex in the whole graph. And if you focus on this thing, so if you start from A, this is just one take for this particular example. If I start from A, I go to C, go to E, then D, then B, then back to A. So in this entire transition, all the vertices of the graph are following a cycle, which means that starting from any vertex, I can go to any other vertex. In other words, that all pairs are strongly connected. So if all pairs are strongly connected, now we can focus on the definition on top of the slide. If every pair of distinct vertices are strongly connected, then we call that kind of graph a strongly connected graph. The question is that is the graph strongly connected? And the answer is yes, because all pairs of this particular graph are strongly connected. Look at the second graph. Are C and D strongly connected? In one of our previous ICPs, we figured out that there was a path from C to D. Is there a path from C to D? Yes. Is there a path from D to C? Yes. So yes, this pair is strongly connected. Answer is yes. Are all pairs strongly connected in this second graph? take a moment, focus on all pairs. If you focus on A, there is no outgoing edge, which means that we can't go to any other vertex from A. So that gives us sufficient evidence that not all pairs are strongly connected. And if not all pairs are strongly connected, is the graph strongly connected? The answer is no, because there is a pair. So for example, AC is a pair which is not strongly connected. AE is a pair which is not strongly connected. There could be many more pairs, like C and B are the pairs which are not strongly connected. So if there is even a single pair which is not strongly connected, then the entire graph cannot be termed as strongly connected. Now, something which similar stuff which we talked about in terms of undirected graphs. So in a diagraph, we say that a strongly connected component of a graph is a maximally strongly connected subgraph. So what is a strongly connected subgraph? If within that subgraph, every vertex, if every pair of vertices is strongly connected, then that is a strongly connected subgraph. And if we make it maximal, which means that no further vertex can be added into that group, into that subgraph, while maintaining its connectivity, then that kind of subgraph is called strongly connected component. So if you focus on this left-hand side example, A has been treated as one subgraph. So this is one component, and this is a strongly connected component. So sometimes I use the term SCC to notate strongly connected components. So A is one strongly connected component, or in other words, A is strongly connected component number one. B is another strongly connected component because it is a maximal strongly connected subgraph. No further vertex can be added into this thing while maintaining its connectivity within the subgraph. And the third strongly connected component is the one which is composed of these three vertices, because they are within that subgraph, all of them are mutually strongly connected pairs. And then this is maximal. We can't add any further fourth vertex into that group. So in other words, the number of strongly connected components in this graph, or sometimes called the cardinality of set of strongly connected components, is 3, which we have figured out in this example. Okay. Let's practice the concept of strongly connected components. Are A and B strongly connected? The answer is no, because we can't go from B to A. There is no path from B to A. So are B and E strongly connected? Yes, because there's a path, direct path in a way, both ways. Is the subgraph induced by JKL strongly connected? So if you focus on these three vertices, they are JKL at the bottom. Is this a strongly connected subgraph? The answer is yes, because within that subgraph, every pair is strongly connected. Is the subgraph induced by the same set of vertices is a strongly connected component? By strongly connected components, we mean that this is maximal subgraph which is strongly connected. In other words, this will be a strongly connected component if we can't add any fourth vertex into this one. So take a moment over here and figure out that is it a strongly connected component. So if you had taken a moment over there, you might have figured out that we can add many more vertices into this. So for example, we can bring in I into this component. From J, we go to I, and from I, we go back to J. So I can be made part of this component. So hence the original subgraph, which was induced by JKL, is not a strongly connected component because it's not maximal. And same applies to G. We can bring in G, we can bring in H, and can we bring in more vertices into this thing? So actually, the number of strongly connected components of that graph are 5, and they have been computed over here. So in this course, we won't be focusing on the algorithmic part of computing strongly connected components, but we just need to understand that what are strongly connected components. They have a lot of beautiful applications. You'll be studying their details in the coming course on data structures, and you'll be implementing them as well. Uh, the complement of a disconnected graph is connected. Think of a graph which is disconnected, which means that, let me first try to build a small and quick analogy that we're talking about. This kind of graph. So we have, when we say disconnected graph, that means that we are talking about a graph which has more than one component. So let's say we have this graph, someone similar to the one which we used in ICPs. Think of its complement. Claim this is a disconnected graph. What will happen with this complement? In complement, we'll drop all these blue edges and we'll connect all those pairs with edges where we don't have edge at the moment. So for example, vertices from the left component will start getting connected with the vertices in the other component. So this will get connected with all other vertices directly because these edges were missing. They will also start getting connected this way. So we'll bring these kind of edges. Now if you focus over here, so you can visually see that the graph, which is made up of these vertices, which are red, these edges which are now red, they are going to represent a graph which is complement of the original graph. So try to formalize this whole thing in the form of a formal definition. Sorry. I hope I didn't miss anything, but like you can see that the graph, if the original graph was a disconnected component, its complement is going to stay connected. Try to, as part of this ICP, try to write this claim in a formal way. Now we are going to have a look at some interesting examples. So this is a story of a ferryman, which you might have heard of before as well. So there is a small river. There is a ferryman with his ferry. On one bank of the river, there are three types of things. One is wolf, the other one is cabbage, the third one is goat. The task for the ferryman is that he has to transport all those three things to the other side of the river using his ferry. So now there are some restrictions. The restrictions are that boat can carry one object with ferryman. So in order to drive the boat, ferryman has to be on the boat. So in other words, only one more object can be loaded on the ferry. So at the start, all those four things, including the ferryman, are on one side. So if ferryman is there, then there's no problem. But if ferryman goes on the other side of the river, then wolf cannot be left alone with the goat. Otherwise, wolf will eat up the goat. And goat cannot be left alone with cabbage. If we leave them alone, goat will eat up the cabbage. So those are the restrictions which we have to keep in mind in order to solve the problem. So I would strongly suggest that take a pause over here and figure out the sequence of steps which you need to take in order to transport all those objects to the other side of the river. So if you had taken a pause over there and you might have figured out some sequence of steps, so such kind of puzzles, and this particular puzzle can be modeled as a graph. So in order to model this as a graph, we represent stair of objects in a vertex, which is encoded like this. So the vertical bars at the start are representing the river. So on the left-hand side, the green part represents one of the items which are on one bank of the river, and the text on the in the red color shows the objects which are which are on the other side of the river. So our start point is this vertex where we have all those four objects: ferryman, wolf, goat, and cabbage on one side of the river. The other side is empty. And one possibility is that ferryman takes, so from this vertex or from this step zero or state zero, we take this edge and we move to a state where ferryman and goat are on one side, wolf and cabbage are on the other side. And from there, we have different possibilities. We can go this way, where goat will be left alone, ferryman will go back, and things will be sorted out that way. And like your entire sequence of steps or different possibilities of solutions are being encoded over here in the graph, and such that each vertex represents a valid configuration of those four objects on both sides of the river. And our ultimate goal is that all those four objects should be transferred on the other side of the river, and the first side, the original side, should be empty. So sometimes we like call this as the first object, the first vertex is called our initial state. So if we model this whole thing as a game or as a puzzle, and we use graphs to solve it. So this first vertex is essentially representing initial state. So this is our starting configuration of the problem. And the last one is our goal state, is the kind of thing where we want to reach. So in other words, our task in terms of graph theory is to figure out a path from this vertex to some valid edges to reach to this thing. So these blue edges are now representing the path which will actually take us to the goal state. So the problem in other words, given a graph which would probably be representing some underlying problem. So in this example, the underlying graph was representing the problem of this transportation puzzle. So our task is to find a path from our initial state to the goal state, from our source, from our home to the target or the destination. So in graph theory, there are different sophisticated algorithms to do this thing. But breadth first search is one of the sophisticated choices which helps us to reach to the goal state. And the algorithm starts with a start, and then it explores all immediate neighbors. So in this case, there's only one neighbor. And then it explores neighbors of neighbors. So when it reaches to the third vertex, then there are three neighbors. So one is the same neighbor which we have just come from. Then there is another neighbor, there's a third neighbor. So in the fourth step, it will explore neighbors of neighbors of neighbors. And as it hits one of the goal states, the algorithm will stop. But again, our task is not really to dive deep into the implementation level details of the algorithm. The objective over here was to introduce you the problems which can be modeled as graphs, and then graph theoretic algorithms help us to address those real-world problems. Another quick example is that if you look at this whole graph, we sometimes call it a directed acyclic graph, which means this is a directed graph. When we say acyclic, that means that it contains no cycles. So if you start from a vertex, you cannot go back to a vertex. So this essentially, this whole map is a map of some undergrad curriculum. So the arrows or edges rotate over here. So for example, if you look at the leftmost part, so college algebra is prereq of trigonometry. Discrete math 1 is prereq of discrete math 2. Programming is prereq of object-oriented programming. So this is a prereq graph. So and intuitively, we can be very sure that it cannot contain cycles because no two courses can be prereq of each other. So this is another example where graphs help us to model different relationships. So, Can there be a cycle? No, we have talked about this thing. So we can apply some sophisticated algorithms again from graph theory, like depth first search and topological sort. So topological sort is a special sorting of vertices, which uses depth first search as a fundamental building block. So it yields an ordering of vertices, uh, which gives us a feasible order for a student to take courses. So for example, if from this entire pool of your entire 4 years curriculum, you can think of computing a feasible order which you would like to take, feasible order of courses you would like to take in a particular order. The topological sort is one such kind of tool which helps us uh, to sort out or output those kind of algorithms. Again, our task is not at the moment to understand the algorithm. The objective was to get introduced to the problem, and the kind of problems which can be modeled as graphs, and the kind of solutions which are quite helpful in our real world. Some more terms about connectivity. A K-connected graph is a connected graph if it remains connected after removing k-1 vertices. And a similar term over here is cut vertex. A vertex whose removal makes the graph disconnected. When we say disconnected, that means that we are increasing the number of connected components. So if you think of connectivity and think of these terms like cut vertex, so just imagine that these different 4 settings of types of graphs or 4 actual graphs are possible layouts of some network. Right? That network could be a power distribution network or some internet network. So which one is a good design choice in your opinion? So if you focus on all of them, so can the first one be a good choice? Not really, because if you just remove this vertex, or if this vertex becomes faulty, your network is going to be disconnected. Same applies to the other second and third choices. But if you focus on the last choice over here, this looks like a relatively good design, because if one particular vertex goes off or becomes faulty, the remaining network is still connected to backup channels. So this looks like a backup good network choice, because it provides good backups. In terms of graph theory, this means that this graph does not have any cut vertex. So there is no critical vertex whose connection will make the graph disconnected. This is another interesting problem or puzzle. So this underlying map is a very old map of some city which is called Königsberg. So the gray parts are the communities living in the city, and the blue part is representing a river which passes through the city, and the green patches are the bridges. The challenge is that we want to tour this city traveling each bridge exactly once, which means that we want to walk through a bridge. We don't want to walk through this bridge twice, and we don't want to miss any bridge. So take a pause. But before you take a pause, if I'm here, I'm just trying to explain the problems. If I use this bridge, I come here. If I use this bridge, I go here. If I use this bridge, I go here. If I use the other bridge, I come here. If I use this bridge, and if I use this bridge, now I can't use any of those used bridges, but this bridge is still unvisited. This is not the kind of stuff which I wanted to have a look at. So can you figure out a path such that we can travel through this city while exhausting or visiting every bridge exactly once? So if you practice that thing, then draw this picture without lifting pencil or retracing. Retracing means that you can't trace a line twice. Give it a try. Take a pause. If you have taken a pause, you might have figured out that that's not an easy game. Okay, irrespective of the answers, can you draw this picture without lifting pencil or retracing? Take a pause. Let me give it a try. If I start from here, go this way, go this way, this time. At least I succeeded with the hope that I didn't lift the pencil, I didn't retrace any line. So, but that was not the kind of case in the previous drawing. Toward this building, passing each door exactly once. So these empty spaces inside the graph are the doors which you can walk through. So take this kind of thing that we want to go from this place to this place, but the challenge is that we have to traverse through each we want to traverse through each door exactly once. So if I start this way, I come here, go this way. And if you keep on following the tracing, am I like really fulfilling the requirement? I should not be passing through a door twice. I should not be missing any door. And now I'm here. And I think I didn't miss any door and I passed through all the doors. I'm sure before starting my drawing, you would have already tried it. So what are all these puzzles? All of them can be modeled as graphs. How? So when we say there's a door, that means that each empty door, each door is an edge that gives us so let me try to model this part as a graph. So this is a vertex. So each space, each location is a vertex. So this is a vertex, this is a vertex. So now when we say there's an edge, there's a door. So this is the kind of connectivity which we need to have. And you can model this whole thing as a graph. And then we are imposing some characteristics on a graph of the kind of drawings which are allowed over here. So if I go to the previous one, so again, these connection points are the vertices. So this is the vertex. This is the vertex. All these lines are edges, and we are talking. So all those connection points are all those joints are modeled as vertices, and then we are talking about different edges over here in the graph. Similar stuff if you want to have a look on the previous one. So all these points where there's a connection, we can make a vertex. So there are so many vertices and there are edges. So an edge is here. There's an edge here, an edge here, some multi-graph. So, and you can model this. So we can model all these columns which we are using as, for examples, as graphs. A closed walk in a graph containing every edge exactly once is called Euler circuit. So Euler was the first mathematician who introduced these kind of puzzles or problems which can be modeled as graphs. So when we say closed walk, that means that we have to go back to the starting point. Or this sometimes we can relax it that if we don't want to go back, then we can call it Euler path, which means that we are talking about a graph which starts from some vertex and goes to some other vertex, but the challenge is that every edge is traversed or used exactly once. That walk contains every edge exactly once. So focus over here is on two things. One thing is every edge. The other thing is exactly once. So no edge is missed. When we say every edge, no edge is missed. Exactly once means that no edge is repeated twice. the kind of thing which we didn't allow. Like you can't retrace. So if this is a vertex, this is a vertex. If I take this path, retracing is not allowed. That's not the kind of thing we want to do. So if you model all these examples which we played with as graphs, so our task is to figure out path of circuit in those graphs. So in other words, like the underlying characteristic of the problem is similar to the ones in other examples. So theorem is that G contains an Euler circuit if and only if every vertex has even degree. So from your first session on graphs, you can recall degree. The total number of edges which are incident on a vertex is the degree. So if and only if every vertex has even degree, then there is a Euler circuit, which means that there is a closed walk where every edge is traversed exactly once. Or it's slightly reduced version where we don't want to go back to the starting point. So G contains an Euler path if and only if it has exactly two vertices of odd degree. So for other than those two vertices, the remaining vertices must be having even degree. So those two vertices of odd and even degree will be the vertices with, so for example, if this is start point, this is the end point. So these two vertices have odd degree. So for example, 1 and 1. So for all other intermediate vertices, they should be having even degree. So if you focus on the intermediate vertices, this vertex has degree 2, this vertex has degree 2, and first and last vertex have degree odd. So hence the Euler path is there, which means that we can find a path where every edge is traversed exactly once. Okay, the last component in this slide set of basics of graphs, we wanted to have a look at the applications. So one like very fancy, attractive, and probably one of the most popular applications is shortest paths. So the kind of stuff which we use every day in using Google Maps or like the transportation services use in terms of like taxi services or air traffic or railway traffic and many more. So each location is modeled as a vertex, and possible routes or roads between them are modeled as edges. So each edge has a weight, which is essentially the distance in terms of kilometers in this particular example, if you look at it. So the underlying the structure which we are extracting from the underlying thing is a weighted graph, and weights are the distances or anything which you want to model on that particular edge. So if you find the different paths from one location to another one, so weight of path is sum of weights of edges which are part of that path. And so then that will give us a weight. So for example, if you look at this graph, from S to G, from a start to the target to the goal, there are different paths. So over here we have colored three paths, blue one, purple one, and the red one. So the first one is from S to A, then B and G. So it's cost is 3 plus 4 plus 8, sum of weights of edges. And same way we have we've added like weights of different edges which are part of the respective paths. With different paths, different costs. When we say shortest path, we are interested in the smallest amongst all of them. So tasks can be completed in directed graphs as well as undirected graphs. So distance from a particle vertex to another vertex is noted as DST. And in our case, we are interested in the shortest distance. So DST represents the way of the shortest path. More specifically, shortest path can be formulated at 3 levels. In the first go, we find the shortest path from a given vertex to another vertex. Then we find the shortest path from a given vertex to all other vertices. And then we generalize it through the entire graph, then we find shortest path from every vertex to every other vertex. There are some sophisticated algorithms available in literature, like the Dijkstra's algorithm, Mandelbrot's algorithm, and Floyd-Warsh's algorithm, which help us to compute these kinds of shortest paths in a directed or undirected graph. We again studying the details and the logistics, implementation level details of these algorithms, their complexities, their trade-offs in your coming course on data structures. Graph is a beautiful concept of graph theory. So the task is to, and over here we're focusing on vertex coloring, is to assign a color to every vertex such that no two adjacent vertices get the same color. And so if we like have huge pool of colors, then we can assign like a lot of colors, practically same number of colors as smaller vertices, then we can assign those colors arbitrarily, where every vertex will be having a different color. The task is to use minimum number of colors. So this minimum number of colors, which is required to color the graph, is called chromatic number of the graph. This is notated as this function, chromatic number of x, equal chromatic number of g. So if you focus on these four visualizations, we have 10 vertices graph. We color it using 6 colors. No adjacent vertices are having the same color. We can use 8 colors. And in the last example, we use 3 colors, and this is what is the chromatic number of this particular graph, because that's the optimal value. So this is a minimum number of colors which are required to color this graph. We can't color this graph using 2 colors. Let's have a look at then why we need coloring in our real life. So for example, if we have this map, so you can treat this entire shape as a map where different regions are shown on the map. So we want to color the regions in such a way that no neighboring colors have the same color. So one way is to model this map as a graph, where each region can be represented as a vertex. So this is the kind of stuff we want to do, but if we model each vertex, we model each region as a vertex, and then we draw an edge between every neighboring colors, every neighboring vertices, then the graph of that particular map will be looking like this. And now our task is to use a coloring algorithm that we can use minimum number of colors to color the vertices. When we are coloring the vertices, that essentially means that we're coloring the underlying type of regions. So, for example, we want to use coloring to model a problem of scheduling an exam such that no student should have 2 exams at the same time. And our task is that how many time slots are needed, right? We are figuring out the optimal number of slots. So for each course, we make a vertex. And if 2 courses have some common students, we make an edge. Now, we are interested in figuring out the number of slots in terms of chromatic number. So when two vertices have the common edge, that means that those 2 vertices cannot be placed in one colored slot. So each color is a slot. So they have to be given 2 different colors. Because there are some common students, those 2 colors and those 2 courses, or in other words, there are some conflicts between those 2 slots, so they can't be placed in one time slot. So we apply the coloring algorithm, we find the chromatic number, and that gives us the minimum number of slots that are required to schedule an exam. This is another example of coloring application. In a cellular network, storage area is divided into hexagonal grids. So hexagonal grid means that this grid essentially represents storage area of a particular antenna which can be deployed over there on a particular frequency. So each adjacent hexagon or region should be having different frequency. And our task is to figure out that what is the minimum number of different frequencies which we need to have in our pool such that we don't end up into the issue of conflicting frequencies. So we model this as a graph. So each region is modeled as graphs. The neighbors are modeled using edges. Now we have this underlying graph. We saw this graph coming column, we find its chromatic number, and that gives us the minimum number of frequencies which are required to model that entire DSM network. Independent set in a graph is a subset of vertices where no two of which are adjacent. So if you look at the first graph is a graph on 12 vertices, which is given as the input. So the next visualization on top, the right on top shows an independent set of size 4. It means we have figured out 4 vertices, no two of them are adjacent. But our task is to find a maximum size, a maximum subset of vertices such that no two in that subset are adjacent. So in this case, there are 5. Why we need to look at these kind of properties of graphs or problems related to graphs? Again, they have different applications. And the computer scientists' foremost task is to, once we know these fundamentals and we face some real-world problem, so our immediate intellectual task will be that how do we model a given real-world problem as a problem in the medical computer science in general, or as a problem in graph theory to be more precise, or what kind of stuff can be modeled as independent set problem or graph problem if we just talk about the kind of topics we are talking today about. The sites are identified for opening restaurants. So some pairs of places shouldn't have the franchises at both of them, so they are very close to each other, or we have some other constraints. So we select K places where we can open restaurants. And in other words, we are interested in finding an independent set containing K locations such that all of them are independent. So similarly, we can use the independent set column in computational biology. It's called single nucleotide polymorphism column. You can like portfolio column on your own. And in the coming slides, like we have this another column which is related to diversifying investment portfolio in economics. Be like more interesting for equal measures or few figures on equal courses. But like the objective over here is not to solve one of those problems, but to show you the diversity of applications which we can have in graph theory. This is a very interesting problem, which is where we are like interested in sending a message from a alphabet to a noisy channel, and getting the maximum independent set actually helps us the maximum number of messages which can be sent, and the kind of set limitations. Click is another type of subset of vertices in a graph such that every 2 vertices are adjacent. In other words, we are looking for the largest click or largest subgraph which is completely connected. So in that subgraph, the vertex is directly connected to the other vertex. For example, if you look at the bottom right here, the graph on yellow or showing a click of size 4. In other words, a subgraph is the maximum or largest size subgraph containing 4 vertices, where every vertex is directly connected to every other vertex in that graph. So again, clicks have different applications in economics, in finance, or in like figuring out some stuff related to financial cards, text detection, text fraud detection, and applications in computational biology. What is stored is in a graph is a subset of vertices such that each edge has at least one endpoint in C in that particular subset. And we are interested in the smallest subset of vertices. So Vertex Tower has again many applications in computer networks, in planning the transmission or broadcasting of different messages or packets over different channels to different network devices. Hamilton path in the graph is a path which contains every vertex exactly once. So unlike Euler path or circuit, while the constraint was on edges, so here the constraint is on vertices. So a Hamiltonian path contains every vertex exactly once. Again, very beautiful application. Where you can use, like people have used these paths to solve different problems in variety of domains. One problem is the problem of finding the longest path in a graph. And it helps us to recognize different handwritten characters and establish their relationships. Handling sales person is the application of Hamiltonian path. Graph coloring is another kind of coloring. In the previous graph coloring, we were focusing more on vertex coloring. In edge coloring, we have to assign a different color to every two adjacent edges such that so if you focus on the graph on the rightmost part of the slide, so no two adjacent edges have the same color. So we are interested in finding the minimum number of colors, we call it edge coloring number of the graph. So again, it has like different applications like scheduling tournaments. In multitasking or multiprocessing. The internet in itself is a graph. So the nodes are different components like physical devices, mobile phones, computers, servers, laptops, and then there are some other specialized nodes like routers, modems, and different other components which are their antennas. They are there which help us to get connected. So it's a quite large and complex communication network, but underlying structure is modeled as graphs where we use graphic algorithms to solve different problems and in indirect analysis. Social networks are another beautiful application of graphs. So the way we get connected on social networks, they make up the graph. And we use different graphic approaches and algorithms to identify different patterns in social networks, like what kind of users are there, which of them are more important across the social network, how they influence each other, how the friends are equivalent over networks. So the graphs have like it's an application in sociology. So these two realizations actually showed up like social behavior, so a social network where like behavioral and graphic approaches are used together to identify interesting patterns. So with the entire web is a huge graph where different web pages are connected to other ones using hyperlinks. And that actually helps us during these search algorithms being deployed by different search engines. So the objective of this last part of the session was to introduce you to a wide variety of applications. And we didn't really want to understand how those applications are working because each of them is going to be a huge subject in itself. But the objective over here in this context was to appreciate the wide range of applications which with the fundamentals of graphs, graph theory, and graph algorithms can be applied. And can be used to solve interesting problems in the domains. So that's it for today. Thank you very much.